Okay, in this tutorial I'm going to use this animation here to talk to you about allosteric enzymes. So let's get started. An allosteric enzyme is an enzyme that's constructed of two or more polypeptide units, and each unit has its own active site. Now the enzyme can change between an active and an inactive state, the inactive here being the brown and the active being the red. So one more time really quickly, here this enzyme has 4 subunits, and each one has its own active site. The red versus the sort of more maroon, so dark color, the red is the active, and this maroony color is the inactive state. So those states, what actually makes them different? It's a slightly different shape. So the enzyme here can change shape slightly between an active and an inactive form. When an activator binds, it stabilizes the active state. An inhibitor stabilizes the inactive state, which means that substrate can't bind to the active site. So again, an activator will bind somewhere and cause the enzyme to, or at least increase the likelihood that the enzyme will be in the active state. Whereas an inhibitor binds, changing the shape of the enzyme so that substrate can't fit into the active sites, and essentially inactivating the enzyme. So actually, the non-competitive inhibitors that we looked at that bind to a regulatory region are actually technically allosteric enzymes. We're getting a change in the shape of the enzyme because of an inhibitor binding to some regulatory region, so that the active site no longer can fit the our substrate. Now, cooperativity or cooperative binding is sometimes when one substrate binds, it may increase the chance of the enzyme assuming the active state. So what this means is, for instance, hemoglobin. When hemoglobin is a molecule, is a protein in our blood that carries oxygen in our red blood cells, and it's made out of 4 subunits. And when one subunit binds oxygen, it increases the chance, or makes the other subunits assume an active conformation, an active shape. So that helps more oxygen to bind. So I guess what this means is it's a cooperative effect. The binding of one oxygen molecule increases the likelihood or the affinity. So it's a word we use sometimes when we're talking about enzymes, the affinity of the substrate for the active site on the other subunits. So basically one oxygen binding makes the protein more likely to assume an active state, which increases the chance of more binding to the other units. And that helps to ensure that when oxygen is in large supply, is in high concentration, like in the lungs, you get a lot of oxygen binding. And the reverse is actually true too. As you start to remove substrate from the active sites, it increases the likelihood that it will go into the inactive state. So as oxygen is offloaded from each subunit, it increases the chance that oxygen from the next one will be offloaded. So in that way it ensures that kind of hemoglobin is either sort of packed full or unloaded. And that's what you want. In the lungs you want to pack it full of oxygen, and then out in the tissues you want to release all that oxygen. So cooperativity or cooperative binding is when the binding of one substrate molecule to the active site causes the remaining subunits to assume the active state or the active conformation, the active shape. So guys, that's basically it for allosteric enzymes. Allosteric inhibitors stabilizing in an inactive shape, allosteric activators stabilizing in an active shape, and then essentially sometimes the substrate itself can sort of act as almost like an activator. So that just helps to ensure that more substrate binds at the other units. Now that's something you probably don't need to know a lot about for your assessments. It really is sort of on the fringe. So not something I'd spend too much time on, but worth maybe just being familiar with just a little bit. It's nothing too crazy or too difficult. Cool, I hope you found that one helpful.